getting into our orbitals, it really all stems back to these atomic fingerprints, which hopefully she talked about, in the Bohr quantum model. So what happened is we made some observations. Those observations are that when we took individual types of elements and we excited the crap out of them, this means we turned them into their gas phase, put them in a trapped container where there was nothing but that species floating around, and then we ran 15,000 volts through them. Okay? As you might expect, they respond oddly, much like if we ran 15,000 volts through us. Probably you're going to get an odd response. And it's likely going to be somewhat unique to each of those individual people. Maybe somebody says, well, 15,000 volts, I don't really care because I can't feel anything. Okay? Maybe somebody's really sensitive to pain and will scream like bloody murder. Okay? Same thing is happening with our elements. But what we ended up noticing is that we didn't get these clean spectrums, a continuous spectrum. We saw lines. Okay? So this is then coming back to, well, what is happening to the element when we pump 15,000 volts of electrons or electricity into them? Well, what's happening is we're taking an electron in that molecule. Don't worry about necessarily where, but we're taking an electron in that molecule, and we're giving it enough energy that it can get to a higher state. It can move upwards. Okay? When it relaxes back down, that energy has to be released somehow. So we've stuck electric energy in, excited up, but now that energy has to get released. Eventually, I have to drop my arm. Okay? When it drops back down, we've now lost that energy. Well, where did that energy go? Okay? When we're looking at the atomic line spectrum, that energy came out as light. Okay? So when we pump this 15,000 volts in, we are now seeing a colored light come out of our sample. And if we break down that spectrum, okay, into the individual rainbow spectrum, pass it through a prism, what we end up seeing are distinct lines, which is kind of interesting. That's a very odd observation. Okay? If we saw a green light and you looked at it through a prism, you would probably just see a big thick band representing that green light. And yet when we take an element and we do the same thing to it, we don't see a band, we see a line of light. And we have multiple lines of light. Well, what's going on here? Okay. The reason we're having those distinct lines is that our electrons can only exist at distinct energy levels, which means when we move from energy level X to energy level Y, I have that energy release, and that corresponds to that jump. But I can't be at energy level X plus a half. Okay? I can only be at that distinct level. This is a staircase. Okay? When we look at a staircase, we place a ball on it. That ball can only exist on each of the flat parts of the step. It can't exist halfway in between the steps. Okay? Because then it's not touching the surface. If we look at a ramp, that ball can be placed on any point on that ramp. Okay? We have a continuous spectrum. When we're looking at our atomic fingerprints, we have these discrete energy levels. So what we're saying with our orbitals is really just, there's a step, and this is where the step is. Where's the next orbital? It's another step, and another step, and another step. Okay? So Bohr's model is just a way of saying these are distinct steps, and we know they're at different energies, and we can quantify that energy. Okay? For those of you going, okay, well, what is that exact energy value? Don't do that. You don't want to answer that question. Okay? That is a lot more difficult than you need to worry about. What you do need to be worried about is that there are distinct steps, and that's explaining our atomic line spectrum. And those line spectrum are just a way of saying that we have a home, we have a place where the electron can exist. Okay? Stupid learning objectives. So this is our quantum mechanical model. We have these distinct orbitals, we have these distinct homes. Okay? They are then arranged according to their energy level. Okay? And if we looked at our electron homes, sorry, I had to skip ahead because I like this slide better. We start with, say, our nucleus down at the bottom, okay, off the screen. We would have our first energy level. Okay? That first energy level is going to be relatively close to the nucleus because our electrons are negatively charged and our nucleus is positively charged. So those electrons are naturally going to get attracted to that positive charge. Okay? So there's a step. How many electrons could I put in that step? Okay. What happens when I put an electron near an electron? They repel. Why are you telling me I can put two there? this gets into kind of more of the complex quantum mechanics of it. Each of those electrons have different spins. They can spin opposite directions, which allows them to get close enough to each other to exist at the same energy level. That's why we can get 2 electrons in our first energy level. Okay? So it seems to run counter to our electron repulsion. But by adding a spin, we can get 2 in. Okay? So we now have the ability to explain the existence of 2 electrons. Okay? Does that explain our periodic table? How many electrons does chlorine have? 17. Remember your atomic number? It's your number of protons, and for the neutral molecule, or the neutral atom, the number of electrons. It has 17 electrons. Well, I just described where 2 electrons can exist. Does this picture accurately reflect the periodic table? No, something's wrong. Okay. Not only is something wrong, but if we look back at Bohr's atomic line spectrum, where does our electron jump from? I only have 1 step. Where do I jump? There's no step. That means there has to be another step. Okay? And there ends up being 7 steps. How do we know there's 7 steps? How many rows in our periodic table? 7 rows. Those bottom 2 may look like 8 and 9, but realize those fit into the middle, right? We only have 7 rows on our periodic table. Those 7 rows are the 7 energy levels of our orbitals. They're just our steps. How many electrons could we fit into one of those energy levels? What do we say at this one? 2. How much should we be able to fit in the next one? Let's go based off of our assumptions so far. If I can only fit 2, then I could fit 2, 2, 2, 2, 2. Which would get me a total of 14 electrons. That is more than 2. That is great. That would get me all the way up to silicon, and I've got a crap ton of other elements to follow after that. So something is still wrong with my orbital description. There has to be something else involved in it. Well, what's that something else? We don't have just these energy levels, but we have sublevels. As we move up in energy, we add a sublevel. So this first one, I have 1 energy, which means I have 1 sublevel. I move up to the second energy, and I now have 2 sublevels. The third? 3. Okay, so I, not exponentially, but increase the potential amounts of electrons. So if we went through and try and scaled that up, okay, we would find that we could put a lot more electrons into our structure. Would we account for all of our elements? I didn't actually do the mathematics on it. No. We still come out well short of covering all of the elements on our periodic table. So there's still something else going on with this. Okay? What happens as we move up to those sublevels?
The number of electrons increases?
I can fit more electrons into a sublevel. Okay? But an individual orbital can only hold 2 electrons. The sublevel is not an orbital, it is a collection of orbitals. Okay? When we start at our first energy level, okay, we want to give that first step or that first type of sublevel a name. Good first name might be first. Okay? Start. I like start. Start is too long of a word, so let's shorten that down. We shorten it down to S. Good choice. So our first energy level has 1 orbital type in it, and it is S. If I want to refer to that specific step, I need to make sure I'm referencing the energy level and the type of orbital. Okay, well, what's the energy level for that first level? 1, because it's, well, first, S, 1s. Okay, what happens when I move up in energy? I'm now at 2 as an energy level. But I now have a new sublevel. Okay? We will repeat what we had in the previous one, so we will have a start of a sublevel. So I will have a 2s. And it will be the lower energy one. What should the next one be? Well, we need a new name. We can't call that one S. We've got to come up with something else. We could call it second. That was a horrible choice because second Begins with S. Okay, so we need a different name for it. What name do we come up with? Principal starts to overlap too much with S, okay, or sorry, with start. Okay, we come up with P. Why did we pick P? Blame the mathematicians and the physicists. Okay, not going to be proton either. Okay, we move up to the next one. Our green one. We're now at the third energy level, but we will repeat our previous. We had an S and we have P. And the new one will be called D, because we know our alphabet so well. Okay. Don't stress behind why we selected those names. Okay. Unfortunately, you just have to know what those names are. And sorry, green didn't show up so well over here. Okay. But like we said already, this still doesn't explain all the electrons we can fit in there. When we move in the 1s and the 2s, they can still only hold 2 electrons. When we jump up to the 2p, this one gets weird. It can hold 6. Well, why can it hold 6? Okay. What this comes from is what I would like to refer to, okay, as an orientation. This is where the shapes of those orbitals becomes relevant. When we look at the 1s orbital, okay, here's another reason why we could call it an s orbital. What is the shape of that s orbital? It is a sphere, which luckily begins with s. When we take a sphere and I rotate it, can you tell I rotated it? No. How many orientations are possible for a sphere? One, which means there is one orbital, which means 2 electrons. That's it. When I move up to the 2s, what happened? Not quite yet. This is still our S. S stood for sphere. It's still a sphere, okay? But it's at a higher energy level, which means it's bigger. That's my attempt at looking at bigger. Here, let's do it this way. What happens when we move up to now the 2p? Okay, it is a higher energy level, and its shape has changed. What is the shape for the p orbital? Okay, a dumbbell. This is where the pinched sphere comes into possibilities. Okay, remember, our orbital orientation comes into play. If I take a sphere or a dumbbell and I rotate that 90 degrees, can you tell me I rotated it?
Yes.
Yes. We have multiple orientations for the dumbbell. We can align the dumbbell along, let's call that the x-axis. We could align it along the y-axis. Or we could align it along the z-axis, which is the one coming in and out of the plane at you. So we now have how many possible orientations? 3. Each of those orientations is an orbital which can hold 2 electrons, but I have 3 possible orbitals. 6 total electrons. That's where the 6 comes from. Okay? This gives us the proper configuration for our periodic table, or the ability to put in enough electrons to account for every single element on our periodic table, and then some. Okay? Where did these come from? It is the quantum mechanical mathematical solve of where an electron can exist. Why is that a difficult thing to process? Electrons exist both as waves and as particles. We have a wave-particle duality, which makes the probability, or makes understanding where they can exist based on probabilities, okay? Not based on a physical existence. This becomes difficult for students to comprehend, because where is the pen, or my pencil thing? Right here in my hand, okay? What is the probability that it is in my mouth? Well, you can see it. There's 0 probability. There is no probability to it because we can physically see that. Okay? Electrons become problematic because we now have to look at them as a probability. We're looking at something that we cannot see, and we have a very hard time predicting both how it's moving and where it's existing. Okay? That's why we have these complex models. We use these models to describe what is happening, and it's ultimately just a way of numbering and labeling where our electrons are. So now when I pick any element on the periodic table, I can say where each of the individual electrons are for that element. It's a labeling system. Okay, you're like, well, this labeling system is impossible. Okay, I don't know, maybe like what state do you live in? What city, what street, what address? When we're looking at our electron configurations, that's all they are. It's an address. Okay? If you just wrote down that I live at 123 Bayview Drive, does that allow you to get to where I live? No. What other information would you need? Crossroads. Okay? A city, a state. Okay? We need all of that information to explain where they exist. And yes, we get all this extra stuff that kind of comes on behind it and try and over-interpret it. All it is an address. Keep it as an address. That's all you're trying to do is identify where your electrons exist. Okay? Yes, they have these pretty pictures associated with them. Deciding on whether or not you want to learn or memorize those pictures kind of comes down to you. Okay? So within our different orbitals, we've got our S, our P, and our D. Okay? You are primarily responsible for S and P. D rarely shows up. If it does, it's typically in 151. Okay? For most of 130, you're concerned about S and P, which is great because the model I gave you, okay, of the energy level, the type, and the orientation works out smoothly and beautifully. A sphere only has one orientation. A dumbbell only has 3 orientations. Why does this become a problem when we move to the d orbitals? What do the d orbitals look like? They have clover leaves. Well, how do you orient a clover leaf in 3-dimensional space? Well, 5 ways. Okay. Well, that's clearly obvious. Only 5 ways. Can't you see that? Okay. No one can. Don't worry about it. That's where the mathematics comes from. Okay. So our individual shapes. We've got our s orbitals, our p orbitals, and our d orbitals. These are here just to give you an idea of what they look like. You're responsible for knowing what that name is. Okay? So for the top one, those are the s orbitals, and they are spheres. The second type of orbital is a p orbital, and it looks like a dumbbell. The third type of orbitals are the d orbitals, and they look like cloverleaf. Okay? Are there more orbital types? Yes. F, G, H. Remember, every energy level you go up, you get a new type. Okay? How many do we have access to? Well, that comes to how the electrons fill into each of those individual orbitals. Okay? Yada, yada, yada. We can overlap them, get our shapes of p orbitals. That's fun stuff. Okay? This kind of gets back to a way to visualize the existence of our electrons. If we put 2 bottles end to end or top to top and trap a fly in there, okay, and we just take pictures of that fly moving, that gets us a rough image of what our orbitals look like. The fly can really only exist within the bottles. And we look at just the pictures. We aren't seeing how it's moving. We just see that it's there. Okay? And if we plotted that out as a probability of where we see the electrons or where we see the fly, we would end up with an image looking much like a dumbbell. Okay? That's the intent of those shapes and sizes and where they're existing. Okay? Putting it all together, this is where you get the number of electrons that can go into each case, and this is where questions can become really nasty, because you can get how many electrons fit in an energy level. Well, the energy level referred to what? The number that we included out front. So in the first energy level, okay, how many types of orbitals do we have? 1. Okay. Of those types, I only have 1 orientation, which means only 2 electrons. When I move to the second energy level, I now have how many types? 2 types. Of those 2 types, okay, do we have multiple orientations? Yes. Which then means we get more electrons going into each of those. Okay, and it kind of scales upward. And we can fall into this trap of trying to look at these and say, oh, how do we process this? How would I ever remember that? You don't have to. This is what the periodic table does very, very well for us. Okay? So,
N supposed to be lowercase or is
Honestly, I had no idea why she was trying to do that. Okay. So our electron configurations are a way of looking at the electrons for any individual element and just specifying the location of every single electron. Okay, so let's keep it simple. Let's start with hydrogen. What is the symbol for hydrogen? H. How many electrons does hydrogen have? Okay, that's a 1. Just agree with me. 1 electron. I want to say where that 1 electron exists. Okay, well, since there's only 1 electron, where could it exist? Where could? Not where it does, where could? Anywhere, period. That 1 electron can be anywhere at once within those different orbital systems. Because there's no orbital that is occupied. There's nothing to prevent it from going anywhere at once. Okay, so it can go anywhere at once. Interestingly enough, when we look at hydrogen, we find that electron tends to go only to 1 space. Where would that 1 space be? Okay, lowest energy level. You all came in here and did what? Sat down. Why aren't you standing? Why do you want to sit? You would get tired by standing because that is a higher energy state. Where do our electrons go? The lowest energy they possibly can, period. Which means when I take that 1 electron and I try and put it into hydrogen, I'm going to place that electron to the lowest energy possible because, by God, it wants to sit down. So where is the lowest energy? Careful, not quite yet, S. Closest to the nucleus, that'll become relevant when we look at a radius. First energy level is 1. What orbital in the first energy level? Now we can bring in our S. I want to specify that there is an electron located in that orbital. Okay, where would I specify the electron presence? So as a possible hint, how about up here? What do we specify there?
That's where the atomic number goes.
That is the atomic mass.
Oh, mass.
Protons and neutrons. Well, protons and neutrons aren't electrons, so they can't possibly go there. Did I flip them? Yeah. Atomic number goes on the bottom. Yeah. So the atomic number then goes in the lower left-hand corner, which is our protons. Okay, well, if that's protons and neutrons and that's protons, those have nothing to do with electrons. Well, I've now occupied those corners. Where do I have left to put electrons? Oh, the other side. Okay, I'll put them right here. There's a good place to put electrons. What do we typically specify in that box? The amount of our species. So if I put a number there, I'd be saying I have 1 1s orbital or 2 1s orbitals. Well, I can't have more than 1 1s orbital. It's always going to be 1. Oh crap, now I'm out of spaces. Where can I put the number of electrons? Oh, that's right. I do have one more space. The upper right-hand corner. Where will you always find information about the number of electrons? Upper right-hand corner. Always, 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 always. Never an exception. Your number of electrons will be determined some way by looking in the upper right-hand corner. So if we're looking for the electron configuration for hydrogen with 1 electron, our answer becomes 1s1 with a superscript. Okay. So let's make this much more challenging. Let's jump to lithium. Said much more, right? So Li, made it a little bit easier. How many electrons does lithium have? 3 electrons. Where does that first electron go? Energy level 1, or lowest energy level. It's then going to go to the lowest energy orbital within that energy level, which happens to be S. So I could say 1s, 1, because I put an electron there. Second electron. Where's the second electron go? The lowest energy level it possibly can, which will be 1 orbital s,
Or still one.
still 1, because we're just saying it's the second electron. Where's the third electron go?
Second energy level.
Why does it not go into the first energy level? The first energy level can only hold 2 electrons. I can't physically put a third one there. Okay? So unlike hydrogen, which could choose from anything, but goes to the lowest, lithium now, that last electron, cannot physically go into the 1s orbital. It has to go to a higher energy level. That's where I would bring in the second energy level. Which orbital type is it going to go into? It's going to go into the s of the two because the s is lower in energy than the p. How many electrons in that s orbital? Just the 1 again. We've now accounted for 3 electrons. How do we know there's 3? Well, this sounds kind of silly, but 1 plus 1 plus 1 equals, well, 3. There we go. There are electrons. That's kind of repetitive, particularly if we had to drop all the way down to, let's even just be nice, fluorine. 9 electrons, I'd need 9 of these individual things. Can I condense this? How do I condense it?
1s with the 2, and then 2s1.
Anywhere where I have repetition, I can condense that and total it. And I get 1s2, 2s1. So I have a way to shorthand this and bring them all together. Okay? That's all the electron configuration is doing. We just keep adding electrons in, keep putting them into the next highest energy level if our previous one is full, and we just keep doing that. That's it. Okay? That's what you're responsible for being able to do.
Do we have to put the 1 there, or can, if you just omit the 1, isn't it just kind of
For
a given?
which one are you referencing?
The 2s.
2s1. I would always include the 1 to remove ambiguity.
Okay.
But in all honesty, is there a standard rule on that? I don't know that. There tends to be, but I don't know. Okay? So, you'll notice that as we went through and did this, we went from 1s, then we moved up to 2s, then we'd fill into the 2p. That makes sense. Okay? Once our second energy level is full, we'd move into the third energy. We'd move to the lowest energy one, which would be our 3s, right? Then that one's full, and we'd move into the 3p, and then we should move into the our third energy level had 3 orbital types, right? S, P, and D. Okay? And because it's the third energy level, it's lower in energy than the fourth. So after 3p, I should expect to see 3d. And instead I see,
Because we only need to know S and P.
nice dodge, but no, I won't use that. Okay? Why do we see that switch? This comes from a massive concept that everybody does not seem to apply or want to apply. It is symmetry-based. Okay? I think symmetry. What does symmetry have to do anything? Think of the most beautiful person you know, or handsome. I don't know, whichever way you want to look at it. Okay? Beyonce. Look at a picture, cover half of her face. Cover the other half. What's the difference between the sides of her face? Virtually nothing. Why is she the most beautiful? Because she's symmetric. We strive for symmetry. What is happening when we fill our electron configurations? We always go to the lowest energy, but what if there's not a large energy difference? Well, then we strive to go for symmetry. And what we end up finding is that when you get high enough in energy, the difference in energy between the 4s and the 3d almost non-existent. But the 4s only has 1 orbital. The 3d had 5. If I put 1 electron into a 4s, is that orbital symmetric? Well, half of it's filled. That's pretty symmetric. Fully filled, half filled, not filled. Okay. I put 1 electron into the 3d. It is now 1/10 filled. It's not half. That's really freaking weird looking. Okay. So what does our electron do? It says, well, that's not pretty for us. You might again go, oh crap, now I have to remember this stupid exchange. No. Again, periodic table does it for you. Okay. It's already set up within the confines of it, okay, which is, I think, hopefully where she's going to be getting to. We already talked about our electron configurations.
Wait, so what you're saying is that it jumps to that orbital?
It jumps to that orbital.
So I have a
Okay.
question. After that picture only went up to 4D, the example, is that because we're not going to get into the higher?
Yes and no. You won't have to worry about going higher. Okay.
It's one of the practice
But-
questions.
Oh, okay. So I lied. You'll have to go higher.
It goes to F. Or-
Okay. Typically, when you look at your fill patterns, you'll see weird charts. Okay, you could see that big long line that we had earlier. Oh man, stupid steps. You could go through and look at this, and that way you'd have to have it memorized. Okay, and that's not super helpful. So we might want an easier way to organize this so we can interpret how it fills. Okay, and we'll come back to the bromine here in just a second. Okay. One way to go through and do it is come up with a chart along these lines. Personally, I would say this is organized flipped because our level 1 is the what energy? Lowest energy, and yet it's at the top of this plot. Okay. People plot things differently, it just kind of depends. This case, Encyclopedia Britannica probably didn't have a chemist write this article. Okay, so we've got it at the highest energy, but if we start with just our first energy level, and then we start writing each of the energy levels underneath it, okay, it's kind of column, nice little grid work. What we can then go through and do is draw this weird diagonal line through it. So we go 1s, 2s, 2p3s, 3p4s. Notice that when we draw that diagonal, it naturally skips the 3D, goes to the 4s first. So we end up seeing, particularly as we shift further out, that we get all sorts of weird fill patterns. Okay? And you would either have to have that memorized, or have this chart drawn out, or interpret our periodic table. Okay? Kind of makes sense?
Yeah, I did it right.
Okay. So let's go back and look at bromine. Let's hide the bromine one. Bromine has 35 electrons, so this is a big one. I know that's already written there. But let's start. First electron goes where? Lowest energy, which would be 1, followed by S. How many electrons can I fit into that 1s? 2. So now I'm going to skip steps and just say I'm going to max that out. Why do I know I have to max it out? Because there's 35 electrons that have to go into this structure. Next energy level.
4S.
Now we jump 4s.
4S2. 3D. Oh, because 5 times 2, right?
Yeah, so for those of you going, holy crap, how are they spitting out these numbers? I think they're just listing off the max number and hoping that eventually they will hit it and I'll stop writing. Okay. So since we're already starting to reach that threshold, maybe we should go through and add that up. So I've got 4 with that 6 gets me to 10. With another 2 gets me 12. With 6, 18. Another 2 is 20. 30. I still need 35 electrons, so it'll be 4p5. Okay. Does that kind of make sense? So some of this required some big memorization already. The s orbital, 2 electrons. You need to know that. Okay. P orbital, p orbital, 6 electrons. You need to know that. Okay. D orbital, 10 electrons, because there's 5 orientations. Each orientation holds 2 electrons, has to have 10 electrons. You need to know that. So knowing how many electrons are necessarily stored in an energy level isn't necessary. What is necessary is knowing the electrons for an individual orbital type. Okay? Why not know for the energy level? Well, if I ask how many electrons are in the 3rd energy level, well, we have the S, which has 2 electrons. I have the P, which has 6, and I have the D, which has 10. I don't need to memorize that the 3rd energy level has 18 electrons. I just have to memorize S, P, and D and add them up. Make sense? Okay. Questions? Really?
Is,
Hey.
the 3D, you know how it goes out of order, is that the only?
No, that is not the only one. It's probably the only one that you're going to run into, just because, again, it's the level of difficulty of the class, though you suggested that there's another problem. If we go through and fill these, we see our first order, 3p to 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s. So as soon as we clear that 3D level, where it first started to go weird, it exponentially just goes further weird. Okay? And you're right, that becomes challenging, which is why you typically aren't responsible for it in this class. That would be 151, where they'd start to ask.
So it's helpful to actually draw this chart. which is pretty simple.
So drawing out this chart can help out.
And then
Yeah.
five.
I have found I'm not very good at grids. I can't draw this chart very well. Okay. But yes, this chart works. We'll talk about another method because there's already a chart given to you. Periodic table. Okay. So how do we use the periodic table? Let's take a look. Hydrogen, what was its electron configuration?
1s.
Sorry, as I find my buttons. Hydrogen, we had 1s1. What was helium?
1s2.
Lithium.
1s2. 2s1.
What's that next one? Beryllium.
1s2. 2s1. Or 2s2.
Boron.
1s2. 2s2. 2p1.
Anybody notice anything? I'm going to run out of space here real quickly. It's a pattern. Let's jump to sodium.
Sodium?
Sodium, I know it's a big one. So we had 1s2, 2s2.
6, that's 10, 3s1. 3p.
Wait, what's above sodium?
Lithium.
What's above lithium?
Helium.
Try again.
Or, sorry, hydrogen.
What's the last orbital, or where's the last electron for rubidium go? Sorry, you may not have that one memorized.
37.
Okay, so if I look at rubidium, I want to know where the very last electron goes.
5s1.
The last electron for 1, 2, 3, 5, S1.
That's because it's on the 5th row.
Why did we say 5?
It's on the 5th row.
5th row. Where was sodium?
3rd row.
3rd row. Where's lithium? 2nd row. Hydrogen.
1.
1st row. Rubidium is in the 5th row, 5th energy level. Okay? It is underneath all of those, and all the ones above it had s orbitals and 1 electron in, so we could do that. Okay? Turns out we get some bigger patterns that come out of this. Yeah. We got blocks of, give me a periodic table. There it is. If we look at our hydrogen, lithium, sodium, and rubidium, they're all in that same column. Well, why were they grouped all in that same column?
Because they all have 1 electron on their outer.
If we look at their outer shell, their last electron is located in the exact same type of orbital, an s orbital. It's at a different energy level, but it's that same type. It's an s. Okay? Which then means when they go to react, they have this 1 electron floating out on the outside of their structure in an s orbital.
So they all react similarly?
They all react similarly, which in theory you guys already talked about when you looked at chemical reactivity at the first part of chapter 5. Okay? They all reacted the same. Well, why did we have those patterns? Because they have the exact same electron shells. Well, why is that important? When I bring two atoms near each other, what's the first thing that interacts? The outermost electrons. That's what determines the chemical reactivity. So when we came up with these patterns where Mendeleev saw that, oh, I had to have these things here, he had no idea what an electron was. Just saw that they reacted the same. We then add the information of electrons now existing, and we find out they react the same, not just because they're magically in the same family, but because they have the same electron configuration. They have the same types of energies of our electrons. That's what allows them to react the same. How many electrons fit in that s orbital?
2.
2. If we look at those first two columns, you'll notice that they kind of stand out different from the rest of the periodic table, right? Okay, why do they stand out different? Because the electrons going into those first two columns are going into the s orbitals. So I can refer to this block of my periodic table as the s block. What happens when I moved up to boron? We looked at its configuration. We had 1s2, 2s2, 2p1. Where did that last electron go? Went into the 2p orbital, which happens to be located in the first column of a separate block than the s orbitals. Why is it a separate block? It's a different orbital. We're now looking at the first element in the p block elements. So that whole block that they've now shaded green is your p block. The last electron for each of those elements will go into a p orbital. Let's take a look at selenium, which, can I figure it out on this chart? 16, oh, geez. Sorry, there we go. Selenium, I think I'm there. Where's the last electron for selenium go? Well, it's a p orbital because it's in the p block. What energy level? I thought you started to say it. It's in the fourth energy level. How do I know it's the fourth energy level? It's in the fourth row. I can start to use the periodic table to locate where that last electron is, which can help me nail down my electron configurations. Okay? At very least in, say, a multiple choice test, which all of your tests are, right? At least your final is. Okay? In a multiple choice test, you can just nail down that last electron, which of the answers matches that. Multiple answers, okay, now I got to work harder. But if there's only one answer, then done. You don't need the rest of the electron configuration. You know where the last electron went. Okay? It's about trying to simplify your approach to looking at it. Make sense? The orange block. How many columns are in that orange block?
9,
1, 2,
10.
3.
Well, I'll just keep minus.
I think that's 10. We've got 10 columns there. Well, how many electrons can I fit into an orbital?
Which orbital?
It doesn't matter. I can only fit 2 electrons into any given orbital. If I can fit 10 electrons in this block, that means there are 5 orbitals. Which type had 5 orbitals? Our D block. We now have the D block. What's in the F block? How many different orientations are there for F orbitals? Careful. There are 14 columns, which means 14 electrons. 7 orbitals, or 7 orientations of our F orbitals. Because I can fit 2 electrons into each one of those orientations. Okay. If we think about the fill patterns, remember if we looked at potassium. Let's clear all that. Look at our electron configuration for potassium. Bear with me, it's going to take a little bit. We had our 1s2, 2s2, 2p2, sorry, 6, 3s2, 3p, numbers. 6, and then 4s. Sorry, my eye's tweaking out. 4s, 1. Why 1? Potassium is in the first column of the S block. Okay? If we look at that fill pattern, that was our fill pattern that we thought was weird. So we thought it should have gone 3D first. Okay? So well, I don't want to have to memorize that. Okay? Well, let's go backwards. 3p6, where's the next electron? If we move, let's look at our numbers. 3p6 gets us to which element? Argon. If we add one more electron, our total number should be 19. Where's element number 19? In the S block and the fourth row. Our electron fill pattern is on the periodic table. You don't need a chart to memorize, it's already there. It's telling you where the electrons are located. You have to recognize that we have the S, the P, and the D blocks. And you can then use that information to determine your fill patterns. Okay? Was that just a mind explosion? Or something
No,
else?
I was just thinking like it would have taken forever. Like our original.
Well, we can hold off on that. Okay? That's what our periodic table gives us. So now let's throw in a monkey wrench on this, because I can see some of you are already like, oh my God, don't do anything worse. Or are you just asleep? Let's make this scandium. SC. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Okay, there can be 10 electrons in the d orbital, but then that would mean I only need one electron in the d block to get me scandium, because right, it's in that first corner, 21. What energy level is that? That is our third energy level. And this is our monkey wrench when it comes to electron configurations, at least in my opinion. Why is that odd?
Because it's the third row of the entire, but it's the first.
Our 3D, our first block, starts with the 3D, even though it is in the fourth row of the periodic table. Okay? Your d orbitals are offset. Okay? This is a repercussion of having to do or show this of our fill pattern. If we tried to slide those 3D orbitals up into the third energy level, what would then happen? We'd go from magnesium to scandium. But magnesium has 12 and scandium has 21. That can't be a single electron addition. Okay? So we have to offset the d orbitals to account for that when we do our filling. So you do have to memorize your d orbitals start at the third energy level. Okay? You will notice that your f orbitals all in addition are offset. Okay? For the same type of reason. Okay? They offset those even further out because we didn't want a massively long periodic table. This gets a little more boxy. Okay? As a shameless plug for organic chemistry, you're looking at this going, that's a lot of things to worry about. Here's what organic chemistry worries about. So erase all those. I'm concerned about that guy. And those, maybe a little bit of those. Rest of the periodic table, I don't care. I don't know anything about it. That's where my focus is. Okay? So it's simple, right? Less elements to have to worry about. Okay? So what we're looking at is those electron configurations and how we can build from those. Okay? Questions on that? I noticed there was some talking up here.
Yeah, I was just getting confused as to how you guys were getting like the 6 and stuff, but I kind of get it now. Because like you guys are good, after you go to like 1s and then 2s, because you're going by columns and then counting how many are in the s, right? And then you jump over to the p and counting how many are in the p, so that's how you get your p6.
So we go, yep. We look at our first row, 1s, 2. That first row is a little bit confusing, so just kind of separate that out. Then we'd move to our second energy level, which would be our 2. S. If I need to get to sodium, sodium's all the way down here. I need to fill that entire row first, so it's going to be 2s2, because I can only fit 2 electrons in. And then it goes to 2p. I have to fill that entire energy level. How many columns are in the p? 6. Each of those columns represents 1 extra electron being added to a p orbital. 2p6, and then I can move down to my 3s1. Other questions? Yes?
So for the D block, it goes 3, 4, 5, 6
Yes.
for the energy levels? Okay.
Yep.
And that's the only block that's off? Like that
Your
one's right
f
here.
orbitals are also off.
Yes.
Remember, your f orbitals insert actually right here.
Right.
So if we actually inserted that, your first f block would actually show up in the 6th row, because it shows up right here.
Okay.
It would actually insert at the 6th row. It's off by 2. Why is it off by 2? The d orbitals offset it by 1, and then the f orbital has to offset by 1 as well. So it totals out to being offset by 2.
Are the noble gases the only ones you can like ensure like argon too?
So I think there's a slide on this, but since you asked it, if we take a look at the electron configuration for sodium, that one's not that bad, but if we're lazy, most of us are, we want to shorthand that. We want to come up with some way to say, I don't want to write that all out. Okay? So I'm going to look at the orbitals that are fully filled. Okay? And I'm actually going to take it a step back from that. I'm going to look at the energy levels that are fully filled. Is the first energy level fully filled? Yes. Second energy level? Yes. Third energy level? The third energy level for sodium, remember, we'd have to count all of our columns across. We'd need 18 to fully fill sodium. I only have 1 electron. So sodium is not fully filled in the third energy level. Okay? So the ones that are fully filled, I'm going to look at those in particular. How many electrons are in that fully filled section? 10. What element has 10 electrons in its ground state? Neon. So if I take the electron configuration for neon, and now I add 1 electron, 3s1, I would now have the configuration for sodium. Extra kind of notational stuff, we'll drop brackets around the neon, and we now have it filled.
And so, yeah, but it was only the noble gases, or you can
When we're looking at our shorthand notation, we only use our elements that have fully filled energies, which is our noble gases. Okay, so you will only use the noble gases officially in the shorthand. Could I have just as easily done, sorry, I defined it. What am I doing? Sodium? Oops. Is this not a valid configuration for sodium? I take fluorine, and I add 2 more electrons.
No, 2p is, like, it's not,
But fluorine's electron configuration accounts for the other 5 p electrons.
But because the electron in the s orbital of the third energy level would want to be at the lowest energy
So
level
the
possible.
But it's still going into a 2p.
It's a 3s1.
That's the extra electron. This accounts for the proper number of electrons and the proper configuration. It is fluorine. If I erased fluorine and I put in its configuration, what would I end up with?
wouldn't the electron in the 3s
So-
orbital want to be in the lowest energy state, so it would go into that 2p orbital? Oh, if you did 2p, that's touche.
I mean, it totals up. Did that look crappy ugly? Based on the rapid response that we got from most of the class, yeah, that looked really crappy, which is why we don't do it. Okay? We focus on our noble gases because those have nice filled shells. We can be happy with those. Theoretically, we could do it with any element. It just makes it look ugly. Okay? Which is why you don't like it. Which I agree. I don't like it either.
Confused, like, because you didn't put 2p, I forgot that fluorine is 2p5.
Yeah. And that's our fluorine. Kind of makes sense? Yes, sorry.
So if you were doing magnesium, you would do Me in the brackets, and then you would put 3s1,
Careful.
or 3s2, sorry.
So magnesium, we go to our previous energy level. Fullest filled is neon. What electrons do we have in addition to neon? Well, I'm in the third energy level, S, second column.
Okay. So I did it, because I went ahead and did
Yep.
it, but
Kind of makes sense?
Yeah.
Okay. Now you can prove it. Whoop, double back. Now you can prove it. Let's see. Can't do helium. That's cheating. Get rid of neon. You can do chlorine and silver. I think we'll get the idea with a couple of these. Do you want practice on your own right now?
Yes.
Do it. Go ahead and take a look. We're going to start with chlorine. We're going to do chlorine. So let's go longhand first. First electron goes where? Lowest energy, which will be our first energy level, and S type. Okay. We could say 1s1. Where's the next electron go? Next electron. Next electron. Next electron. This is going to get a bit redundant and repetitive, right? Okay. But that's what's happening. We're slowly adding those electrons in and accounting for that. Okay. So our first kind of shortcut is to say, I have to add more electrons than will fill the 1s orbital. So I'm just going to jump straight to filling it, 1s2. I have to add more electrons than will fill, or than can fit in the 2s orbital. So I'm going to fill it. I have to add more electrons than will fill, right? Chlorine, yes. 2p6. I have to add more electrons than will fill 3p5. Okay, why do I slow down at that 3p5? I look at the row where chlorine is. It's in the third row. That means anything with a 3 in front of it, I need to be a little bit more careful on. Okay? I can't just automatically fill it with electrons. Okay? I will start at the left and work right. Okay? This would be our longhand. For those of you that don't like the longhand, can go through and look at this and say, okay, where do I have a fully stable structure or fully filled? You might jump and say all the way to the 3s2. That is fully filled. Okay? The reason we don't use that 3s2 in it is that we're looking at our fully filled energy level, and even that kind of runs into some kind of questionable areas later on too. Really what we're applying is our noble gases. Why do we call them our noble gases? Because they're royal hoity-toity jerks that don't want to interact with anybody. That's why we're using them as our electron configurations, okay, as our shorthand, because we're saying this stuff isn't doing anything. This stuff is. Okay? That's the big difference. So we go through and say, okay, where do I have a noble gas configuration? Well, when I fill that p orbital, I've got my noble gas, and I can shorthand that as, remember the 3s2 gets you to magnesium. Our electron configuration, we can't include, if you did neon 3p5, neon has how many electrons? 10.
You have to include, even though it's like implied, you have to include it in the electron configuration.
It's not implied. Neon does not have 3s2 electrons. They are not there. They are not implied. You have to specify those. Okay? So this comes from looking at what the electron configuration is versus the highest energy electrons. So previously we just looked at identifying the highest energy electron, where was it located, and left with it at that. To get the full electron configuration, you have to show it all. You can't just say what's the highest energy one. You need to show everything. Okay? So as our check, neon comes in with 10 electrons. The 3s2 gets us 2 electrons. The 3p5 gets us 5 electrons.
I think all these new rules, I would rather just write it out.
Some people want to write it all the way out, some people want to keep it shorthand. Ultimately, neither really matters because you never do it in chemistry. This is the only time you do it. And I recorded that. That's good. Questions? Kind of get it? Should we go through and look at silver?
Why not?
Okay. Why not? Because this is boring. And I don't want to look at it. Okay, silver. We'll start longhand. 1s2.
2s2, 2p6, 3s2, 3p6,
Whoops, sorry.
3p6, 4s2,
Wait,
4s2.
why did we jump to 4s2 after 3p6?
Because 3p and 4s are
Use your periodic table to go through. There's our 3p6 at argon. The very next electron goes to 4s. The periodic table tells you the fill pattern. You don't have to have anything memorized. It's right there. The next electron to go from argon plus 1 electron is potassium. Potassium with 19 electrons is in the 4s. You don't need to memorize that 4s comes before 3d. After we fill the 4s, what's the very next electron do? Go into the d block. We have to remember, this is the part you have to remember, that you have to be offset by 1 for our energy level. There's our 3d. Okay. And that's going to be fully filled. What's the very next orbital we encounter? 4p. We completely fill that. The next one. The next one. It's 9. Oh, it is. 40. Sorry. I don't memorize. 49. So for those of you that liked the longhand, or rather liked the shorthand, you're probably like, God, that was dumb. Why did we do all that? Okay? Because we want to see all the pieces. If you want the shorthand, what we would do is take a look at silver, look at the previous row, krypton. So we are looking for this stupid gray thing. It's irritating. We are looking for the krypton configuration, which ends at which energy? 1, 2, 3. It ends at 36, true, but that's in the just the 4th energy level, our p-orbitals. And we end up with our configuration of krypton 5s2, 4d9. So for those of you insisting that shorthand is awful, come on. You can't make the argument that that is easier to do the longhand. I mean, the shorthand is significantly shorter, okay, in this case.
Understand the longhand.
Okay.
I got both.
So, just be aware, limitations in both. Ultimately, the biggest thing you're responsible for is you need to recognize that part outside of the noble gas. That last part is looking at our valence electrons, our outermost electrons. Why do we care about the outermost electrons? We bring 2 atoms near each other. The first thing that encounters the outermost electrons. Those are our valence electrons. What's going to determine the radius of an atom? The outermost electrons. Okay. What's going to determine the ionization energy? Ionization energy is the ability to remove electrons from an atom. It's the outermost electrons. So we are concerned primarily with the outermost electrons. Those are the ones that dictate the chemistry for every one of our elements.
Ionization energy is that just describe its ability to form an bond? Well, the ones with higher electronegativity have lower ionization energy.
We'll sort of address that. Predicting valence electrons, this will become super, super important. Chlorine, so we could figure it out by looking at their electron configurations. Again, let's take a look at chlorine. And for those of you that just said periodic table, yes. Yes, the periodic table does give it to you. I don't know why I picked chlorine. That one's big. 3s2, 3p5. Okay. Our valence electrons are the ones that would be outside of our noble gas notation. So our valence electrons are, Come on. 3s2, 3p5. How many electrons are outside the noble gas notation? 7. What column is chlorine in? Block, P block 5. Well, that's not 7. Okay. Look at the tiny little numbers at the very top of that column. It says 17. That's 7 versus 17. That's not too bad. What's the Roman numerals? 5 and 2, also known as 7. Where are your valence electrons? They are the column title in the Roman numerals. You know how to read Roman numerals? You know the valence electrons. How many valence electrons does nitrogen have? 5. If we go through and look at the electron configuration for nitrogen, she's going to hate me. I didn't cover enough material. 1s2, 2s2, 2p, 3. Our noble gas notation. How many electrons in that valence? In that valence, 2 plus 3, 5. What was our column for nitrogen? 5. Our valence electrons are on the periodic table. Okay? So I do want to get through just a little bit. I know. Okay, I need to cover. I'm going to pause it on this. So, dumb, but there it is. So I'm just going to move on because it's really that bad. Atomic radius and metallic character. Okay, you should already know your metallic character trends. Where are your metals? Left side of the periodic table. Where are your nonmetals? Right side of the periodic table. Okay, notice that diagonal running through the middle where you run into the semi-metals. The lower left is your most metallic. The upper right is the least metallic. There's your trend. Atomic radius transitions with that. There are weird things that pop up within it. Your atomic radius is dependent on the electron configurations. The more electrons you have to the higher energy levels, the bigger it gets because the electrons are higher in energy. What if they aren't higher in energy? If you put electrons at the exact same distance, what happens? Here's my nucleus. Here's an electron. I put another electron in. Exact same distance. What happened to the radius? Didn't change. That's it. Didn't change. Same energy level, right? So as I go from lithium to beryllium, what happened to the energy level? Didn't change. What happens to the radius? Doesn't change. But if we look here, it says it decreases. Why does it decrease? What else is changing when we add that second electron as we go from lithium to beryllium? It's easier than that. What is the difference between lithium and beryllium? Electrons, yeah, but that's not going to change it. I can add electrons, I can remove electrons. It's still lithium, it's still beryllium. What makes it lithium? What makes it beryllium? The number of protons is what determines the element. When we move from lithium to beryllium, what happened to the number of protons? It increased. I put my electrons at the exact same distance. But what happens to the strength of the nucleus? It gets stronger. What does that mean happens? The electrons get sucked in. Okay? That is your explanation for left to right. Because it doesn't make sense otherwise. You add more electrons, it should get bigger. Okay? It doesn't get bigger because you're putting them at the exact same energy level. It gets smaller because you have a stronger nucleus. Knowing why, you're questionably responsible for. Knowing the answer, absolutely, you need to know. Okay? Same concept comes back to, I know. Ionization energy, exact same deal. Come on, where's my slide? Okay? You can use ionization energy and electron configurations to predict those trends. The further the electron is from the nucleus, what happens to the amount of energy necessary to rip it away? It takes less. Okay?
Wait, then how is electronegativity stronger?
Electronegativity, you can talk to me after class about that because you're not officially responsible for one person. So ionization energy is looking at ripping those electrons away. Same idea. It all comes back to those electron configurations. Ultimately, what you are responsible for is the memorization of those rules for atomic radius, metallic character, and ionization energy. I will tell her to go over those three concepts again, but I have to stop there, unfortunately.